Okay. Okay. Now we'll start with this types of beams: determinate, indeterminate, bending moment, shear force, and for simply supported and cantilever and overhanging. From this, we will come to know that simply supported beam, cantilever, and overhanging. Only these three beams are mentioned in the syllabus. Means they are interested in only determinate structures. Okay, they are interested in only determinate structures. They are not interested in indeterminate structures. Why? Because indeterminate structures, this concept will come in B level. In B level. Okay. For prelims paper 1, for paper 1 we will study only determinate structures. Okay. Now this syllabus, and after that, now first we will study types of supports. Types of supports. Okay. Now look at here. The first support is simple support. Simple support means we have some columns here. Above that, a beam is kept. Just it is kept. It is not connected. It is not welded. It is not pinned. Nothing is done. Just it is kept on two columns or walls. Then this is called as a simple support. It is not simply support. It is called simple support. Okay. For your information, you should know what is simple support. Right? If this is a simple support, then we will be having a reaction. How many reactions? Just vertical reactions we will be having. That is this vertical reaction, and this is another vertical reaction. Okay, we will be having two reactions. You can call it as a RA and you can call it as a RB. Two reactions we will be having. Only two. Right? Then after that we will be having another support, that is called as a roller support. Roller support. Okay, roller support. When you see the roller support, it looks like this. It look like this. Okay, so here very interestingly, here at the top you are seeing one point here, and beam will come from here. Means at this point this is hinged. Okay, don't call it as a hinge support, but it is pinned here. That one beam and this support both are pinned at a particular point, and there is a roller here. Okay, if I push in this direction, it moves in this direction. If I push in this direction, then it will move in the horizontal direction. But if I push in the vertical direction, then there won't be any motion in the vertical direction. Therefore, I will be considering I will be considering only one reaction for this one, that is your RA. Only one reaction will be there for roller support. Okay. Notation for roller support is they may be like this. Sometimes they may be like this with this. Okay, these two are roller support. Even sometimes the roller support can be inclined also. See, this is your roller support. In this case, support reaction will be perpendicular to the surface. Perpendicular to the surface. That is your RA. Therefore, always a support reaction is perpendicular to the surface. Sometimes, if this is a wall, they will provide you roller support like this also. Okay. Then in this case, this is your support. Correct? This is all about roller support. Now, hinge support. One more thing. Here, you should remember whenever I say roller support, reaction is 1. Reaction is 1. Okay, now? Then freedom is 2. Freedom means what? Here, the freedom means the roller support can move in horizontal direction, that is one freedom, and roller support can rotate about one particular beam. So about one particular point. See, this handle or this beam can rotate freely, it can rotate, right? Then the rotation is 2. Therefore, they will ask you question, then how many freedoms are there in roller support, or what are those? The two freedoms are there in a roller support, and what are those? One rotation and one translation. Transition. Okay, transition. That is, transition means x direction or y direction in a linear, and rotation is a rotation. Okay, then one rotation and one transition. Then these two reactions freedoms will be there, and one reaction will be there. This is complete. Now we have another support. That's another support is the hinge support. Okay, it look like this. Means here it is pinned, and at the bottom it is fixed. It's not completely fixed, but it is fixed. Okay, now how many reactions will be having? We will be having two reactions. One is perpendicular to the surface, one is parallel to the surface. You remember like this: one is perpendicular to the surface and one is parallel to the surface. Okay, if hinge support is like this, then what happens? If hinge is like this, then support reactions will be: one is perpendicular to the surface and one is parallel to the surface. Okay, direction don't worry, you can call it as the RA and this one as a HA. Okay, one is perpendicular and one is parallel. Right? The notations, it can be like this also, like this also. This is a hinge support. Sometimes they will show you only one hinge like this, and your member will come from here. Okay, this is also hinge support. Okay, now if I talk about reactions, two reactions are there. Two reactions are there. One vertical will now we'll call it one perpendicular to the surface and one parallel to the surface. Okay, then freedom. How many freedoms are there here? Freedoms are rotation. Okay, if I rotate this arm or this beam, then it can rotate. Here also it can rotate. It can rotate. Here also this handle can rotate. This handle can rotate. Okay, therefore we have one freedom. We have one freedom. What is which freedom it is? Rotational freedom. Rotational freedom. And restriction, two transitional restrictions are there. This and this horizontal restrictions are there. This is your hinge support. When I come to the fixed support, the notation is something like this. Actually, usually it will be like this: the beam and some portion will be inside the wall. This is your fixed support. But usually we will show it like this. Then here there will be three reactions. One is parallel to the surface, one is perpendicular to the surface, and one is rotation. Okay, fixity may be like this also. In this case also, you will be having perpendicular to the surface, parallel to the surface, and rotation. Three reactions will be there. Reactions, three are there. Correct? Then what about freedom? Freedom, zero freedom is there. Okay, there is no freedom for the fixed support. Notation, only one notation we have. Just we will show it like this. Okay, this is your fixed support. Okay, now we learned about three types of support. The first one is simple support, just ignore it. And the second one is roller support, and the we'll call this one as the first one. And the second one is hinge support, and the third one is fixed support. Apart from these, there are some other supports. They are called as hybrid supports. Okay, this you will study in UG level, not in diploma level. Okay, hybrid supports. For your understanding, I will show you. This is a hybrid support. Okay. Now you might be wondering, this is a roller support. No, this is not a roller support. Why? Because one member and which is welded at this point, and after that we have a roller here. Okay. Here the reactions will be, it will not move in a vertical direction and it will not rotate about the z axis. Therefore, two reactions are there. That is RA and this is MA. Okay, no? But it can move. What is the freedom for this one? Freedom is one freedom, and that is horizontal. Horizontal freedom is there for this one. This is one hybrid support. And we have another hybrid support like one hybrid support. Another hybrid support is the same thing. You can show it here also. Okay, this is also the same hybrid support. And another hybrid support is something like this. This is your member. Now inside I will be providing rollers. Okay, this is another type of hybrid support. Here what happens, you can just use your common sense, you will come to know what all reactions are there. If I put a load, then it won't come down, therefore there is a vertical reaction is there, call it as the Ra. And if I put a load, then it will not take any load because it will move. And if I apply some moment, then it will resist the moment, therefore two reactions are there, Ra and Ma, two reactions are there. Then freedom is horizontal, freedom is there, right? These are your supports. Now supports is complete. If you have any doubt, you can ask. Okay, now we'll go to the next one. Next we will study types of loads. Okay, types of loads. Types of loads, the first one is point load. Point load is also called as concentrated load, which is indicated by an arrow with the pointer. The unit is kilonewton and the direction of arrow indicates the direction of the force, and usually the length of the arrow indicates the magnitude, but nowadays we are not using any graphical methods, therefore the length of the arrow is not considered. Okay, now this is your point load. Okay, very interestingly, we know how to handle point load. We know how to handle point load, but we don't know other loads how to handle. Okay, we don't know how to handle other loads, therefore every loads we have to convert to point load. This you remember. The second one is uniformly distributed load. Uniformly distributed load is also called as UDL. Okay, UDL. This is also called as rectangular load. Why rectangular load? Because the correct representation of this load is this rectangular shape. Okay, but we this takes a lot of time to write like this, therefore we are using this notation. Okay, this is your UDL. Actually we have to measure this way. Okay, if this is a rectangular load, then this is your length of the rectangular load L, and the height of the rectangle is W. Height of the rectangle is W. Now very interestingly, how to convert a point this UDL into a point load? For that we will be having dotted line showing the point load, and the value of the point load is W into L. Value of the point load is area of the this one, and this will be acting at a distance L by 2 from one end, and other end is also L by 2. This is also the same one, therefore this is a W and this is a W into L. This is L by 2, this is L by 2. Right? Okay, I am going a little fast because you already know all of them, just I am revising the things. Okay, now coming to third one, UVL. UVL, that is uniformly varying load. Uniformly varying load, or UVL. Okay, here this is also called as triangular load. This is also called as triangular load. Okay, why? Because the shape is in triangle form, right angle triangle. Now the height of the triangle is W, and the length of the triangle load is L. Then convert this one into a point load. Then when we convert this one into a point load, this will be, that point load will be W, capital W is equal to half into base into height, or WL by 2. Okay, this is your converted point load. Very interestingly, this acts at a distance, at a distance L by 3 from the highest point, that is, this is L by 3, and from here it is 2L by 3. It is 2L by 3. Right? Okay. See here, many students they will make mistakes when they consider this one. See here, where is the CG of this triangle if I ask? Then you just look at this right angle, and near to the right angle mark one dot. Near to the right angle make a dot. When you make a dot near to the right angle, then from that point this is a 1/3 of length, and bigger one is 2/3 of length. Okay. Now can you tell me where is the CG of this one, this triangle? The CG of this triangle, first you have to mark this one, then near to that point you will mark. Then after that this distance is 1/3 and this distance is 2/3. Okay, students do mistakes like this. They will write a triangle, then after that they will write a CG here, and after that they will get a confusion which side is 1/3 and which side is 2/3. This is a wrong practice. Okay, you mark it near to the right angle, that point, then after that you determine the CG of the point. Right? Now you concentrate on this point, this load. Okay, the height is W, length is L, and point load is WL by 2, acting at a distance L by 3 and 2L by 3 from either ends. Right? These are your three types of loads. Over. Now coming to types of beams. Types of beams. Okay, types of beams. Beams, we have to consider a support and a member, then we have to club them. Okay, supports, we have a roller support and hinge support and fixed support. We want a support, and after that we want member. Member means that is a horizontal beam, horizontal member. This is a beam. Now we have to make some arrangements, like say for example this is one beam with two side roller, with two side roller. Okay, this is having a two reactions. This is unstable, unstable beam. Unstable, why? Because when I apply some load, horizontal load, this beam will move. Okay, this is not stable, it will move in this direction. Correct? Second one is, if I take a beam, this one, then if I provide here hinge support and here hinge support, 2 inch support if I give, then what happens? There will be two reactions. The one is vertical here, horizontal here, horizontal here. Okay. Now, if I apply some horizontal force, the beam will not move. Means the beam is stable. The beam is stable. But the beam is stable. But if temperature increases, then unnecessary stresses will induce. Unnecessary stresses will induce. Correct? Therefore, we will not consider such beams. This is also not considered. Then which is a simplest and good beam? Which is a very simplest and which is very good one, means determinate. Okay. Good in the sense of in terms of a beam with one side hinge and another side roller. Okay, this beam is considered as a simple beam. Therefore, it is simply supported beam. This is simply supported beam. Why? Because if I apply horizontal force, then this part will be fixed one. It will not allow it to move, but this part will move. Therefore, there won't be any deflection or unnecessary stresses in the beam. Then if I apply vertical load, then it will resist in the vertical direction. Okay. Therefore, this is simplest beam and simply supported beam. Okay, that's why we will be seeing everywhere in the civil engineering. The first thing what we consider is simply supported, because it will satisfy all our requirements and some calculation part, this one application parts also. Okay, then after that we have another beam. That beam is called as, sorry, this simply supported beam only I will consider extended portion of the beam will be there at one side. See here, this side it is extended. Then this portion here, this portion I will call it as a overhang. Overhang. Then this big beam is called as overhanging beam. Or specifically you can call it as a one side overhanging beam. One side overhanging beam. Right? Then you will be having two side overhanging beams also. See here, this is your two side overhanging beam. Okay, both the side overhanging is there. Okay, this is also simply supported overhanging, simply supported one side overhanging, simply supported both side overhanging. Next we have another beam, simple beam, that is your cantilever. This cantilever will be look like this. The portion of the cantilever is inside the wall, or you will just call it as a cantilever beam. Okay, this cantilever beam, as we already discussed, there will be three reactions, and it is fixed at one end and free at other end. This is cantilever. Now beams we have studied. Then after that, one minute I will explain the other beam, other type also here. other than these three Other than these three means simply supported and cantilever and overhanging. Other than these three beams, whatever the beam you draw, that is called as a continuous beam. Continuous beam. Okay, even fixed beam also in some textbooks they will consider continuous beam. Why? Because indeterminate, that I will cover later. Okay, apart from this, outside the box I will draw one more beam, that is your fixed beam. Okay, this is fixed both the end. Why it is outside, that you will understand later. Okay, now, okay, how continuous beams looks? There will be number of spans like this. Okay, here it might be hinge, here it might be roller, and here it might be hinge. This is your continuous beam. Right on. Okay, now we have discussed beams by their supports. Okay, simple support, cantilever, or overhanging, continuous. Okay, now beams in a structural point of view. Structural point of view. Point of view. Okay, in your syllabus, in this one diploma syllabus, we don't have anything like statically indeterminate and kinematic indeterminate. No? Therefore, B students are not introduced to these. Sorry, diploma students, they don't know about these two. Therefore, that is not included. However, you as a engineering students, if you are engineering student, then you will be knowing these two. Therefore, you can just refresh those concepts. Here, it is not required that much. Okay, now look at here. We have two types of beams based on structural point of view, that is determinate beam. Determinate beam. The second one is indeterminate beam. Indeterminate beam. Okay, now what is determinate beam? Determinate beam is if number of equations, number of equilibrium equations equal to number of reactions. Number of reactions. Then what is indeterminate beam? The number of reactions are greater than number of equations. Okay, you just remember this one. If you are a B students, you will understand it. Okay, one example I will show you, that is for simply supported beam, how many reactions are there here? We have one reaction and one reaction here, another reaction here. 1, 2, and 3. Therefore, reactions are 3. Okay, how many equations we want to solve this one? We want summation of fx equal to 0, summation of fy equal to 0, summation of mz equal to 0. Now, three unknowns, three equations are there. Therefore, equations equal to 3. Therefore, these two are equal based on this condition. Therefore, simply supported beam is determinate beam. Simply supported beam is determinate beam. Now, if I consider fixed beam this side, then how many reactions are there here? Vertical reaction, horizontal reaction, vertical reaction, horizontal reaction, moment here, moment here. 3 reactions here, 3 reactions here. R equal to 3. Then equilibrium equations, again 3. So R equal to 6. Then again 3. Therefore, number of reactions are more than number of equations. Therefore, fixed beam is fixed beam is indeterminate beam. Indeterminate beam. Okay. Now, examples of examples of determinate beams. Determinate beams. The first one is simply supported beam. Simply supported. And the second one is cantilever. Cantilever. Next, overhanging. Overhanging. Simply supported. 1, 2, and 3. Any doubts?
No, sir.
Okay. Now we'll go ahead with the slowly. We will go ahead with the shear force and bending moment. Okay. Now, okay. Look at here. Force means a point load will be there. This is called as a force. Okay. If a force is going upward, then we will consider it as a positive. If a force is going downward, then we will consider it as a negative. If a force is going rightward, then that is positive. If a force is going leftward, that is a negative. Right? I am discussing about force. Very, very important. That is force. Then the combination of these forces will be something like this. Look at here. This is one force and this is another force. Okay. Now don't call this one as this is a positive, sir. This is negative, sir. No, don't call like this. These two together creating tension in compression in the member. Therefore, compression we will call it as the negative. Then, if another body subjected to this force and this force, then that body is called as a positive. Here, don't see individual force. Don't see individual force. See the combined effect on the body. Very interesting. Combined effect on the body. Correct? Tension positive, compression negative. Okay, now don't see left side, right side. Like that. Now look at here. If this is the body and this is the line of action, and for this line of action, if I apply one force this direction and one force this direction or reverse, you know, then this body is getting compressed. It is get body compressed. Now similarly, look at this diagram. This is a body and this is your axis, but this time the forces are not acting the earlier. One force is acting like this, half arrow, and another force is acting like this. Okay, now this force and this force, these two force, in between there is a small gap, very small gap, very small gap. Then these two will slide, this force and this force, this force and this force will slide each other. When they slide each other, they create shear. They create shear. Sliding is called as shear. Therefore, this reaction, this diagram is called as a shear force diagram. Shear force. This is your shear force. Feel the difference between this and this one. This is shear. This is compression. Understood? Okay. Means if any body is like this, then this is the axis of the body. Then if I have one force in this direction and one force in this direction, then this body is subjected to what? Shear force. This body is here subjected to shear force. Now that arrow I will put it here and another arrow I will put it here. Right? This is here, this is here. Now, right? In some textbook they will write it like this: one arrow here, one arrow here. Then, if this is the case, combined effect, then this is called as a positive shear. This is called as a positive shear. Correct? For that, you will remember it like if this is your axis, here the blue line axis is there, no? That axis if I write, then right side, this is your right side, and this is your left side. Okay, right side downward is a positive, left side upward is a negative. Sorry, positive. LUP. You can remember this one. Left up positive. Look, left up positive is LUP. Similarly, the same I can get in a other direction also. This is upside and this is downside. This is also creating shear in the body, but this shear is a negative shear. Therefore, if you have an axis like this, then this axis, this is the right side, this is the left side. Therefore, right up negative, run. You remember these two notations. Run means right up negative, look means left up positive. Okay, this is the sign convention. Whenever we calculate shear stress, shear force, then upward positive, downward negative, no, don't call like that. Upward positive, downward negative is gone. Now we are talking about shear force. Therefore, shear force means left side, right side. You have to talk. Left up, left down, right down. Like that you have to speak. Right? Now you got the difference between force, combined effect of force, and shear force. Normal force and shear force. Right? Okay. Now we'll go to the next page. Here we'll understand moment. Moment. See here, if I have this nut and this nut is connected to pana. You know, see this is a nut now, like this. Okay. Then if I apply the force, then it will start rotating. Okay. This will rotate in this direction and this nut also rotates in this direction. This is called as a moment. Whether this pana is bending? No, the pana is not bending. right? Therefore this is simply called as a moment, not bending moment. Okay, now moment, how to consider moment? Clockwise direction positive, anti-clockwise direction negative. Only we have a two conventions, positive and negative. Okay, if I want to bend this stick, this is one stick, I want to bend this one. To bend this one, I will apply one moment here and another moment here. When I apply two moments, the stick will bend like this. Okay, this is bent like this, means where I applied one moment here and one moment here. This is your stick, the section in the stick. Then this action is called as positive bending moment or sagging bending moment. This action is called as sagging bending moment. Now I can bend this stick even in the other direction also by applying in other direction moments like this. Then this is one moment and this is another moment. Then this is your section. This structure or this bend is called as negative bending moment or hogging bending moment. Okay, whenever you study, that's why you feel the difference between this one and this one. Okay, here moment, only moment, clockwise, anti-clockwise. But this is bending moment. In bending moment, the beam or stick tend to bend, but in moment, beam or stick will rotate, tend to rotate, tend to rotate. Right? That's why you have to have the difference between these two. That's why whenever you determine bending moment, clockwise, anti-clockwise ಅನ್ಬಾರ್ದು. Bending moment calculate ಮಾಡಬೇಕಾದ್ರೆ clockwise, anti-clockwise, no, you should not pronounce like that. Bending moment means sagging, hogging. Okay, na? Then only moment means that is clockwise, anti-clockwise. This is our sign conventions we will be using. Right? Now, what is the shear force? Shear force is algebraic sum of all vertical forces, vertical forces, either left side or right side of the section, right side of the section. See here, if we have one beam like this, the first thing is what? First thing is you should know the support reaction, and after that, very important thing is you should mention the section. Where is the section? This is your section. Correct? This is your section. Now after mentioning the section, you have to look at either left side or right side. You have a choice. You have a choice card R. You look at either this side or this side. Don't look at both sides. Now if you are looking at this side, if you are looking at this side, then add all vertical force over. That is your shear force. That is your shear force. Okay. If you are looking at this side, the same procedure you follow. You follow any one procedure, either this side or that side. Don't look at both sides. Okay, no. This is your shear force. Adding is there, no? That adding is called as algebraic sum. I will show you with the problem. Just you remember the definition. Now bending moment, that is algebraic sum of all moments, either 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 left side or right side of the section. Okay. Here also, if this is a beam, then you have to first mark the section as per the statement section. Then after that, you look at this side or this side, either this side or this side. Then all the moments either left side or right side of the section. Don't look at both sides. Here moments we want. Add all moments. All moments. All moments means what? Force into perpendicular distance. That is your moments. Okay now? We will solve one problem so that you will understand how to determine the bending moment. Okay now? Till now, do you have any doubt? Just 30 seconds. Okay. Now, I will give you one problem. We'll do one thing because we are preparing for competitive exams and with less time. That's why I will give you some standard beams with standard loads and we will write down bending moment diagram for bending moment and shear force value and diagram for those. You know, that will be very easy. And later we will, if you are interested, because conventional however we are not seeing, we are going through only objective type questions now. That's why we will be seeing directly. Okay, first I will revise this notes already shared. Go through that notes. I will explain that one through this notes only, so that later you can read. This is what explained. This is they explained about first we will understand what is the shear force and bending moment. Understanding the shear force and bending moment, this you can read it. See that bending, how it bends, how it shears and all they have mentioned. And here they have given you sign conventions. Okay, sagging.
Sir, voice break ಆಗತ್ತೆ sir.
Voice break ಆಗುತ್ತದ? 1 minute. Okay, now you check it. Now is it clear?
Yes, sir.
Okay, right. Okay. Here we discussed about the sign conventions for shear force and bending moment. We already discussed. You can read this document. Then after that, shear force definition they have given here, and again sign conventions explained very neatly. Bending moment, positive bending moment and negative bending moment, they have given explanation. Okay, and this is a negative bending moment. You can read this one. Okay, this one we will concentrate first, and later I will come to because we will instead of solving 10 marks question or 8 marks question problems, no big problems and drawing the Bending diagram, that we will cover in this one when you qualify paper 1. When we start preparation for paper 2, then we will solve big problems. Okay, before that, whatever that is required for 1 mark question, that we will discuss. See here, this is very very interesting and very important. Many times in GATE or in any competitive exams ask this concept. Whatever I explain now, you just go through. Look at here. This is a beam. Okay, don't forget this one. This is a very important concept. Later you will come to know. Some loads are there. I don't know which type of load. Some loads are there. Correct? Now this beam will have bending moment diagram. Something like this. Okay, don't worry about the shape. This is your BMD, not RMD, just BMD. Okay? Now we will be having shear force diagram. Whatever it is, I don't know the value, just it is a shear force diagram. Correct? This is SMD. Now, very interestingly, this will have a deflection diagram. Let us consider this is your deflection curve. Deflection curve means after application of the load, the beam will take this shape. The beam will take this shape. Okay, now in this shape, when the beam takes this shape, then at any particular point, let us consider this point is a point, sorry, C point. Let us consider C point, and this distance is called as deflection. This point is called as, that distance is called as deflection. Deflection is denoted as y. Okay, at that particular point, bending moment is there, that is your m. Okay, at that particular point you have shear force, that is your shear force, yes, sf. Okay, at that particular point you have load also, no, that load l. Okay, now remember, what are those? L is a load, m is a bending moment, sf is a shear force, y is a deflection. Correct? Y is a deflection. Now after that, one more thing, here at this point, at a point, if I draw, right, at this point if I draw one tangent, then it will take this shape, and that theta, that slope, the tangent, if I draw, that slope will be there, that slope is called as theta. Okay, now we will establish a relation between them. Now look at here, how I write, you also practice in the same way. Right from the bottom, y means deflection, y means deflection, dy by dx means theta, means slope. Correct? Next, d square y by dx square means m by ei. M by ei means bending moment diagram. Bending moment diagram. Okay, now d cube y by dx cube means shear force. Shear force. Now d power 4 by dx power 4 is equal to load. Okay, remember this one. Okay, this is very important. Okay, now you don't have any doubt in y. Y means deflection, correct? Y means deflection. Look at here, dy by dx, what we can call it is a differentiation of deflection is, they will give option. Okay, differentiation of deflection. Okay, they can ask you, they can tell you like this also, rate of change of deflection. Rate of change of deflection means dy by dx. Okay, rate of change of deflection. Okay, next, integration of ulta. See here, this is differentiated, this is differentiated, this is differentiated, this is differentiated. Correct? Rate of change of deflection, slope. Rate of change of slope, bending moment. Rate of change of bending moment, shear force. Rate of change of shear force, load. Correct? Now another color, black color. Now look at it. Double differentiation of deflection is bending moment. Double differentiation of theta is slope. Double differentiation of bending moment is load. Double. Correct? Triple differentiation of shear force is deflection is shear force. Triple differentiation of theta is load. Correct? Now all arrows were upward direction. Now I will use all arrows downward direction. Okay, this green, concentrate on green. Integration of load is shear force. Integration of shear force, bending moment. Integration of bending moment, theta. Integration of theta, deflection. Correct? Double integration of load, bending moment. Double integration of shear force, theta. Double integration of bending moment, deflection. Correct? If you go upward, differentiation. If you go downward, integration. Correct? Now, differentiation is also called as rate of change of. Rate of change of. Rate of change of. Integration is also called as summation. Is called as summation of. Okay. Now I will ask you few questions. Will you answer? You can unmute your mic and you can answer. Right? Now, rate of change of bending moment is called
Shear force.
Shear force.
rate of change of bending moment is shear force. Okay. Rate of change of slope.
Bending
Bending
moment.
moment.
Okay. Rate of change of shear force.
Load, sir.
Okay. Rate of change of deflection.
Slope, sir.
Okay. Summation of shear force.
Bending moment.
Okay. Addition of load.
Shear force.
Okay. Sum of all the vertical forces.
Shear force.
Now you got it now. Sum of all the vertical forces means sum of all the loads. That is integration of load. That is your shear force. Just below that one is there. Okay. Means if you have you can do it like this also. Sum of all the shear force, bending moment. Sum of all the bending moment, slope. Sum of all the slopes, deflection.
Deflection.
Correct? This you have to remember. Now we'll go to the PDF. Now it is very easy. Right? A relation between the shear force and bending moment and load. Okay. Where we got this one? Y was there, theta was there, bending moment was there, SF was there, and load was there. They want the relation between these three. Now you can see rate of change of this one. Okay. One more thing. Look at here. d, d power 4y by dx power 4 can also be written as d by dx of d cube y by dx cube. Correct? Now, in this one, what we said here, d cube y by dx cube means what? Shear force. Correct? Now, come here. Therefore, d by dx of this is nothing but shear force over. That is what written here. Then this is your load. This is your load. Therefore, this box is dv by dx is load. Why it is minus, that don't worry. Okay. Now the same thing, rate of change of moment is shear force. We can look at here, rate of change of moment is shear force. Correct? Like that. This is the relation between these three. Next, procedure for drawing shear force and bending moment diagram, you can read them. Construction for bending moment diagram, you can read. Difference between the loading and their shear force diagram. Okay. From here we will study. We will study some standard figures only. Okay. Now look at here. First I will study cantilever because it is very easier than simply supported beam. Okay, we'll finish all of them. Now look at here. If I apply moment at free end, okay, then shear force diagram is this. No shear force diagram because no vertical force. Then bending moment diagram is this. This is M, this is M, and this is negative. This is M. Okay, I will remember this one. Any doubt? Okay. This is called as pure bending. Why pure bending? Because no shear force. Only bending is there. Therefore, that is called as a pure bending. Okay, they may ask you in exam. Give an example for pure bending. ನಾಲ್ಕು ಆಪ್ಷನ್ ಯಾವ್ದಾರ ಆಪ್ಷನ್ ಕೊಡ್ಬೋದು. Now, this is a pure bending. Okay. They may ask you something like this. In pure bending beam, which of the following is zero? Four options. Shear force is zero, bending moment is zero, slope is zero, deflection is zero. Shear force is zero. In pure bending beam, at any point shear force is zero. Right? Like that they can ask you questions. Right? We'll go to second beam. This is first beam. The second beam is cantilever beam, point load P. Then shear force diagram is constant P. P. Bending moment diagram is PL. Okay, this is your second diagram. Right? You just by heart these equations. Next. Okay, here what are the remarks? Remarks is shear force constant. Shear force constant. Okay, then you will get this one. Third beam. Third beam is UDL of W. Then shear force diagram is sorry. Shear force diagram is this one. This is WL. And bending moment diagram is this one. Okay, WL by 2. Okay, this is linear. This is linear. This is parabola. कौन बोला? Parabola. Right? Now, fourth one. Fourth one. Cantilever UVL. Right? Next. Shear force diagram is parabola. Shear force diagram is parabola. Okay. Even in ಬರೆಯೋ you can write it like this also. Wait. Like this also. Okay. Just sign conventions. This is parabola. Next. ಏನಾಯ್ತು? Next, this is cubical. Cubic parabola. This is cubic parabola. This value is WL by 2. This value is WL by 6. Okay. 4 diagrams over. Next one. Next we'll come to simply supported beams. Simply supported beam. Point load middle W. Support reaction W by 2. W by 2. because this is L by 2, this is L by 2. Shear force diagram is, see here, shear force diagram, very interesting, I will tell you. Here this arrow is upside, no? Go up, yes, go up, no load, straight, come down, go straight, then this arrow says go up. Yes, this is shear force. Then bending moment diagram is, this is your bending moment diagram. Shear force diagram and support reaction both are same. W by 2, W by 2, negative, positive, positive. Then this height is WL by 4. Okay, by heart these things. Next, simply supported beam, simply supported beam, point load eccentric, A, B. This is WB by L, this is WA by L. Okay, shear force diagram. Now, this arrow says go up, constant, come down, go straight, up. This is shear force. Then this support reaction is here, and this support reaction value is here. Now, bending moment diagram is at this point peak. This height is WAB by L. Okay, na? Now, like that, there are many. I will show you in the diagram now. We'll come to this one because, however, you will be reading this notes later also. Once again, this cantilever subjected to point load. Therefore, this is a P constant and a triangle. Correct? UDL. This is the UDL. UDL means cantilever triangle. WL. This is WL square by 2 parabola. Hmm. Next, interesting. See here which type of beam they have given. One force P here, one force P here. P and P. For this shear force diagram is, look at here. This arrow says go come down. Yes, come down. Then go straight. Then this arrow says go up. Over. This is your shear force diagram. SF. What is the value? P. And this is also P. Bending moment diagram is something like this and like this. This is PA and this is PA. This is 0. Okay. Return. Now there is a problem here. This problem you can just solve it like this. Later you can solve. This is UDL 1 and this is 1, this is 1 cantilever. Right? You can split and solve. This we, however, you will be doing this one later when you start this one. Yeah, paper 2. Okay. Now this is your cantilever subjected to UVL, already studied, right? UVL. This is your UVL and shear force diagram, parabola and cubic. Now WL square by 6, WL by 2. Okay. Reverse UVL. Hang barಬೋದು ನೋಡ್ರಿ. This is your UVL. Okay, na? Shear force is again same, parabola, sorry, concave parabola, convex parabola, like this parabola. Value is same, WL by 2. Agar ಇದು ಹೆಂಗಿತ್ತು? Look at here. Both differences you can feel. The other diagram was like this. Okay. For this parabola was like this. but value is same, WL by 2, this is also WL by 2, but this is concave parabola, this convex parabola, this is concave parabola. Okay. Then this is same, here the bending moment diagram is like this one, correct? Here the value is WL by 6, but here in this case WL by WL square by WL square by 6, WL square by 3, which is bigger? WL square by 3 is bigger or WL square by 6 is bigger? Hmm?
WL square by 3, sir.
Very good. This is bigger. Why? Because now look at here. This load is here now. This side is very huge. Means it will bend a very lot. No, it will bend very curvedly. That's all. Now very interesting. It is already studied. Okay, cantilever subjected to just a point load. Now see shear force diagram. Is there any diagram for that? No diagram. Then bending moment is constant. Okay. Now point load. Point load means this is W by 2, this is P by 2, this is P by 2, this is P by 2. Then shear force diagram is this one, like this. Okay. Then bending moment diagram is PL by 4. Then this is PB by L, and this is PA by L. Okay. Then for that diagram is portion, that depends on portion. You see, this is a bigger portion, smaller portion. This support reaction will be here, this support reaction will be here. Then this is PAB by L. Okay. Now very interesting, 2-point load. This is A distance, this is A distance. Okay, this is A distance and this is A distance. 2-point load. Then support reaction very easy. In such case symmetry is there, no? Therefore this is P, this is P. When these two are P, see this one will spend time here. This is P and this is P, correct? Now look at here, this P and this P, this P and this P, this is P, this is P. Two equal and opposite forces, is called as what? Couple. This is couple. Wherever there is a moment, constant. Right. Am I audible? Right. Now, here there is a couple now. At that place, you are getting shear force constant. Already we saw one problem, and here also this is there. See, this portion shear force is affected in this portion. This load shear force is affected in this portion. Then nothing is left in between. Therefore, shear force diagram is not coming. Correct? Why? Because this force and this force they rotate, and this force and this force they rotate. They are not acting any shear force in this zone. Now G shear force is constant, 0. When shear force is 0, then bending moment is constant. This you have to remember. Shear force is constant, then bending moment is, sir, shear force is 0, then bending moment is constant. Okay. I will give you another example. Rate of change of bending moment is what? Rate of change of bending moment is
Slope.
I. Rate of change of bending moment is shear force.
Shear force.
Right? Now, if rate of change of bending moment, that bending moment is something constant, then what is the differentiation of constant? Correct? Differentiation of constant is 0. Means when bending moment is constant, then shear force is 0. That is here. Bending moment is constant, shear force is 0. Correct? Okay. Now UDL, this is W, therefore this is WL by 2 and this is WL by 2. Now for that diagram is, shear force diagram is, go up, come down, then go up. W by 2, W by 2, WL square by 8. This parabola. This is parabola. Now this problem is there, you can solve later. UVL. Okay, UVL. Then support reactions we want. What is the support reaction? RA, WL by 6, and this is WL by 3. WL by 6, WL by 3. Okay, this is bigger, this is smaller, that's why smaller side and bigger side. For this bending moment diagram is, you remember this one. In SSC also it is asked many times that what is the shear force diagram, shear force value in the support, at the support, or shear force value at the support is WL by 6, WL by 3, WL by 6, WL by 3. That will come here and that will come here. Right? Maximum bending moment in this case is this one, W L square by 9 root 3. Always remember this. Next, this one. In such case, symmetric UVL. Support reaction is what? WL by 4, WL by 4. Interesting, no? When simply supported beam is point load, it has now its bending moment diagram is WL by 4. When load is like this, then here WL by 4. Suma hint ನೆನಪಿಟ್ಕೊಳ್ಳಿ. ಪಾಯಿಂಟ್ ಲೋಡ್ ಇದ್ದಾಗ ಇದು WL by 4 ಡುಮ್ ಡುಮುಕ್, ಇದು W ಇದ್ದಾಗ ಇದು WL by 4 ಡುಮ್ ಡುಮುಕ್. ಆಯ್ತಾ? Like that you can remember. Okay, now then shear force WL by 4, WL by 4. Height WL square by 12, WL square by 12. ಕರೆಕ್ಟಾ? ಹೆಂಗ್ ಅಂತ ನೋಡಿ, ಹಿಂಗ ಉಲ್ಟಾ. Okay, in this case very interesting ಬರ್ತದೆ. ಹಿಂಗೆ ಬರ್ತದೆ, ಕಾನ್ಸ್ಟೆಂಟ್ ಆಗ್ತದೆ, ಮತ್ತು ಹಿಂಗೆ ಬಂದು ಹಿಂಗೆ ಆಗುತ್ತೆ. Then WL by 4, WL by 4. shear force bending diagram ಹಿಂಗೆ ಹೋಗ್ತೈತಿ, ನಮಸ್ಕಾರ ಮಾಡ್ತೈತಿ. WL square by 24, ಅರ್ಧ, half. WL square by 12 ಇರ್ತದೆ ಆಗಲೇ, WL square by 24. Okay, if you have a load like W1 and W2 here, then you can have equation L by 6 2 W1 W2, L by 6 W1 2 W. ಒಂದ್ಸತಿ ಇದಕ್ಕೆ 2 ಮಲ್ಟಿಪ್ಲೈ ಮಾಡೋದು, ಒಂದ್ಸತಿ ಇದಕ್ಕೆ 2 ಮಲ್ಟಿಪ್ಲೈ ಮಾಡೋದು. ಕರೆಕ್ಟಾ? L by 6 ಫಿಕ್ಸ್ ಇಡೋದ, ಒಂದ್ಸತಿ 2 W1 ಮಾಡೋದು, W1 2 ಮಲ್ಟಿಪ್ಲೈ ಮಾಡೋದು, ಒಂದು ಹಂಗೆ ಇಡೋದು. ಇಲ್ಲಿ L by 6 ಹಂಗೆ ಇಡೋದ, W1 ಹಂಗೆ ಇಡೋದು, 2 W2 ಮಾಡೋದು. ಕರೆಕ್ಟಾ? ನೆಕ್ಸ್ಟ್ ಹೈಟ್ ಬರ್ದಿಲ್ಲಲ್ಲ ಇವ, ಹೈಟ್ ಬರಂಗಿಲ್ಲ. ಯಾಕೆ ಬರಂಗಿಲ್ಲ? ಸಿಯರ್ ವೆರಿ ಇಂಟ್ರೆಸ್ಟಿಂಗ್. ಈ ಡಯಾಗ್ರಾಮಿಗೆ ದೆನ್ ಈ ಡಯಾಗ್ರಾಮ್ ಬೇಡ, ಇದು ಬೇಡ. ಈ ಡಯಾಗ್ರಾಮ್ಗೆ ಇಲ್ಲಿ ಸ್ವಲ್ಪ ಹುಷಾರಾಗಿ ನೋಡ್ರಿ. ಈಗ ಒಂದ್ಸತಿ ಓಕೆ, ಈ ಡಯಾಗ್ರಾಮ್ ಅದು ಸೆಂಟರ್, ಇದು ಎಕ್ಸ್ ಐತಲ್ಲ, ಇದೇನೈತಲ್ಲ ಅದು L by 6 WL by 3, ಇವೆರಡು ಈ ಕಡೆ ಅದ. ಬಟ್ ಇಲ್ಲಿ ಮಿಡಲ್ ಇಲ್ಲಿದು This is not L by 2. This is not L by 2. This is X. X is L by root 3. Very important. L by root 3. This maximum is not in the middle. It is not in the middle. It is at a distance L by root 3. Right? Now, from this you can get an idea that shear force, wherever shear force is 0, bending moment is max. Correct? Shear force is 0, bending moment is max. ಆಗಲ್ಲ ಏನು ಕನ್ಕ್ಲೂಷನ್ ಮಾಡಿದ್ವಿ? Bending moment is constant, shear force is 0. ಎರಡು ನೆನ್ಪಿಟ್ಕೋಬೇಕು. Next, the same way that diagram here, not here, here again triangle came, no? That's why this is not in the center. This is not in the center. Right? They have not identified this distance because it is very complicated. That's why X is not given. Now this is extraordinary case. Sometimes they may ask this way W is there, no load is varying with this equation. In that case, this is WL by pi, then maximum is WL square by pi square. Just by heart. This is very interesting. Simply supported beam with the moment middle or at a distance A. Okay, if for that bending moment diagram is like this. See here, simply supported beam, bending moment inside, then shear force is this one, bending moment is something like this. Very interesting. This is M by L into A, M by L into B. This is M by L, this is M by L. Over. These are all extraordinary problems, you can solve them. And here indeterminate structures are there, but it is not mentioned for SSC syllabus. Right? Indeterminate fixed beams. And here reactions are there, you can by heart. Over. This is not required. Whatever I told, no, that is written here. They have drawn here. ನಾವು ಆಲ್ರೆಡಿ ಮೊದಲೇ ಹೇಳಿವಿ, ಅವ್ರು ಇಲ್ಲಿ ಹೇಳಕತ್ತಾರೆ ನೋಡಿ. ಕರೆಕ್ಟಾ? They have told it like this. Y is the deflection, dy by dx is theta, over differentiation m, shear force to load. Correct? Now objective type questions are there. We'll take 10 minutes break. Then after that we'll last half an hour we'll solve some 1 mark questions. If you have any doubts you can ask. 1 minute I'll stay here for any doubts. Okay, now it is 9:53. Correct? Exact 10 o'clock will start. We'll start. Question number 127. Unmute yourself and go on answering. Beam which is fixed at one end and free at other end is called cantilever beam. A beam supported at its both ends is not simply supported beam. Correct answer. Beam extending beyond the support is called beyond the support is called overhanging beam. Beam encasted at both the ends is called encasted means fixed beam. Beam supported on more than two supports is called continuous beam. Cantilever beam is one which is fixed at both ends. No, fixed at one end, free at other end. Correct. Supported at its ends. No, supported more than two supports. No. Next, simply supported beam is one which is supported on more than two supports. No, false. False. This is right. False. An overhanging beam must overhang on both sides. Wrong. Mustn't. No, must. Fixed beam is one which is fixed at both. Continuous beam is one which is fixed at one end, free at other, supported more than two. Concentrated load is one which acts at a point on a beam. Right. Spreads? No. Spreads? No. Where is no? A load which acts at a point on beam is called as uniform distributed load. At a point, disagree. Uniform distributed load assumed to behave like a point load at the center of gravity of the load for all sort of calculations. Correct. Load which is spread over a beam in such a manner that it varies uniformly over the whole length of the beam is called uniformly varying load. Shear force at a point on a beam is algebraic sum of either forces in the left side or right side. Bending moment at a point on a beam is algebraic sum of moments on either side of the point. Bending moment on a section is maximum where shear force is headed.
0.
0.
Bending moment on a section is maximum, then shear force is 0. Then shear force at a certain point on a beam changes sign from positive to negative, and vice versa. Bending moment at a point will be 0. True or false?
False.
Hmm? Bending moment is 0 antidana. Bending moment is actually maximum there. Therefore false. When a load on the free end of a cantilever beam is increased, failure will occur.
So B.
B. Fixed end. Correct answer. Bending moment at a free end of a cantilever beam is
0.
correct answer. Next. Cantilever beam of a length L carrying point load W at a free end is shown in the figure. Which of the following is correct? ಇದು ಕೊಟ್ಟರೆ ಇಲ್ಲಿ cantilever beam point load. ಇದಕ್ಕೆ ಯಾವ್ದು ಬೇಕಂತ which of the following is correct? A is a bending moment diagram of C, and C is the shear force diagram. ಇದಕ್ಕೆ ಫಸ್ಟ್ ಈ ಕಡೆ ಹಾಕಿಬಿಡಲ್ಲ. This is point load. For the shear force is this one. For this bending moment is this one. Okay. A is a bending moment diagram. Wrong. A is a shear force diagram. Correct. C is a bending moment diagram. Correct. B is a bending moment diagram. Wrong. Wrong. Then B is a shear force diagram. Wrong. Therefore, B is answer. When a cantilever beam is loaded with concentrated loads, the bending moment diagram will be
Inclined.
inclined. No. See here, a cantilever beam is loaded with concentrated load. One load illi, one load illi, one load illi. Correct. Inclined is the correct one. No? Then bending moment diagram will be okay. ಇದು ಹಿಂಗೆ ಬರ್ತಾ ಮತ್ತೆ ಹಿಂಗೆ ಬರ್ತಾ ಮತ್ತೆ ಹಿಂಗೆ ಬರ್ತಾ ಹಿಂಗೆ ಬರ್ತಾ okay, inclined straight lines. Next, bending moment diagram for cantilever beam loaded with uniformly distributed load will be parabolic curve. Correct? Next, maximum bending moment of a cantilever beam as shown in figure 2.4.1 lies at 2.4.1 ಇದೆ ಅದನ್ನೇ ಇನ್ನೊಂದು ಕೇಳೋಣ ಎಲ್ಲಿ ಸಿಗ್ತಾ maximum bending moment at a fixed end. The shear force of cantilever beam shown in that one. Correct?
Sir, the 150th question free and ಆಗಂಗಿಲ್ಲ sir.
Maximum bending moment of a cantilever beam as shown in the figure. Maximum bending moment in cantilever is always fixed end, no? See, this is the load.
Yes sir, yes sir.
Okay. Now, shear force of a cantilever beam as shown in the figure, same figure. Either the shear force angle. This one. 0 at the free end and W at the fixed end. Wrong. W at the free end and 0 at the fixed end. Wrong. W throughout the length. Right. WL throughout the length. Wrong. Next. Shear force of a cantilever beam of a length L carrying uniformly distributed load W per unit length is cantilever beam. Correct. WL. Correct. This is your uniform distributed load. Shear force diagram they want. Okay, this is WL. Therefore D. Shear force of a cantilever beam carrying uniform distributed load W unit by ಫ್ರೀ ಎಂಡ್ ಕೇಳೋಣ 0 ಹಾಕ್ಬೇಕು ಫಿಕ್ಸ್ಡ್ ಎಂಡ್ ಕೇಳಿದಾಗ WL ಹಾಕ್ಬೇಕು shear force diagram for a cantilever beam of length carrying uniformly distributed load W per unit length will be right angle triangle shear force diagram UDL ಗೆ Correct answer. Equilateral triangle ಅಲ್ಲ. Isosceles ಅಲ್ಲ. Rectangle ಅಲ್ಲ. Bending moment of a cantilever beam of length L carrying uniform distributed load W per length at free end. Bending moment diagram ಕೇಳಕತ್ತೇನೆ ಈಗ. W at free end is 0. ಕೇಳಕತ್ತೇವ. Next. Shear force and bending moment are 0 at the free end of a cantilever beam. If it carries point load at a free end, no. Point load at the free end ಬಂತಂದ್ರ shear force diagram ಹಿಂಗ್ ಬರ್ತೈತಿ. Therefore ಅವ ಏನಂತಾನ shear force ಮತ್ತು bending moment ಎರಡೂ 0 ಇರಬೇಕಂತ. One option wrong. Point load at a middle of the length. Point load middle of its length ಹಿಂಗಿತ್ತು ಅಂದ್ರ ಇದ್ರದ್ದು shear force diagram ಹಿಂಗ್ ಬರ್ತೈತಿ. Bending moment diagram ಹಿಂಗ್ ಬರ್ತೈತಿ. Shear force bending moment are 0 at a free end of a cantilever beam if it carries. Okay, ಇದು ಆಗ್ಬೋದು ಒಂದು ಸ್ವಲ್ಪ ಆಗ್ತದೆ. Uniform distributed load over the whole length. Shear force diagram. Bending moment diagram. ಇದನ್ನು ಆಯ್ತಲ್ಲ ಕರೆಕ್ಟ್ ಐತಿ ಇದು ಕರೆಕ್ಟ್. ನನ್ ಆಫ್ ದಿ ಅಬೌವ್. ಈಗ ಇವೆರಡರೊಳಗೆ ಯೋಚನೆ ಮಾಡಿದ್ರೆ ಇದನ್ನ ಬಿಡೋಣ ಇದನ್ನ ಹಾಕೋಣ. ಯಾಕ ಗೊತ್ತಿಲ್ಲ. ಅದ ಹಿಂಗ್ ಕ್ವಶನ್ ಕೇಳಬಾರ್ದು ನಾವು. This question is not valid. Bending moment of a cantilever beam of length L and carries uniform distributed load at fixed end ಎಷ್ಟಿರ್ತೈತಿ? W square by 2. Maximum bending moment of a cantilever beam of length L and carrying uniformly distributed load W unit length lies at the middle of its length. True, false? False. Shear force diagram for a cantilever beam of length L carrying gradually varying load from 0 at free end and W per unit length at a fixed end is.
So parabolic.
Next. Bending moment diagram for a cantilever beam of length L. Cantilever ಮತ್ತೆ bending moment diagram. Length L carrying gradually varying load from 0 at free and W this one at the fixed end is parabolic. Disagree. Correct? Because it should be cubic. Shear force of a cantilever beam of L carrying gradually varying load from 0 to W is shear force UVL ಗೆ ಎಷ್ಟು WL by 2.
WL by 2.
Correct. WL by 2. Correct? Next. Bending moment diagram. Same thing. Bending moment diagram. For a cantilever length. Fixed. At its free end. Fixed end. correct? W square by 6. Bending moment at a point of a simply supported beam will be 0. At ends of the simply supported beam is 0, correct?
Yes.
Maximum bending moment of simply supported beam of span L. Carrying
So WL by 4.
WL by 4. Bending moment diagram for simply supported beam loaded in its center.
Isosceles triangle.
Isosceles triangle. Isosceles triangle meaning ಎರಡು ಸೈಡ್ ಸೇಮ್ ಇರ್ತದ. Correct. Okay. Maximum bending moment of simply supported beam with central point load lies at the point of loading. Correct. Maximum bending moment ಎಲ್ಲಿರ್ತದ, ಪಾಯಿಂಟ್ ಲೋಡ್ ಎಲ್ಲಿರ್ತದ ಅಲ್ಲಿರ್ತದೆ. Shear force of a simply supported beam carrying central point load changes sign its midpoint. Correct.
Correct.
Okay. Simply supported beam is shown in the figure. The bending moment diagram will be
Sorry.
A. Correct. Shear force in the center of the simply supported beam carrying uniformly distributed load over of W. Shear force ಕೇಳೋಣ simply supported beam ಗೆ UDL ಗೆ. Center of the ಕೇಳೋಣ.
So 0.
Very good. Bending moment in the center of the simply supported beam. Bending moment ಕೇಳೋಣ center of the simply supported ಕೇಳೋಣ UDL ಗೆ.
WL square by 8.
Very good. Next, shear force at the end of the simply supported beam. Okay, shear force ಕೇಳೋಣ at the end ಕೇಳೋಣ. Carrying uniformly distributed load. ಕರೆಕ್ಟಾ? ನೆಕ್ಸ್ಟ್ ಶಿಯರ್ ಫೋರ್ಸ್ ಡಯಾಗ್ರಾಮ್ ಕೇಳೋಣ ಸಿಂಪ್ಲಿ ಸಪೋರ್ಟೆಡ್ ಬೀಮ್ಗೆ UDL ಅಲ್ಲ. ಏನಾಯ್ತು?
Sir, voice ಕೇಳಿಸ್ವಲ್ತ್ರಿ.
ವಾಯ್ಸ್ ಕೇಳಾಯ್ತಾ? ಒಂದು ನಿಮಿಷ.
No, sir.
ಓಕೆ, ಈಗ ಕೇಳ್ಬೋದಾ? ಕೇಳ್ತಾ ಈಗ ವಾಯ್ಸ್?
Yes, sir.
ಓಕೆ, ಏನ್ ಹೇಳ್ತಿದ್ದು? ಶಿಯರ್ ಫೋರ್ಸ್ ಡಯಾಗ್ರಾಮ್ ಸಿಂಪ್ಲಿ ಸಪೋರ್ಟೆಡ್ ಬೀಮ್ ಕ್ಯಾರಿಂಗ್ ಯೂನಿಫಾರ್ಮ್ಲಿ ಡಿಸ್ಟ್ರಿಬ್ಯೂಟೆಡ್ ಲೋಡ್. ಮೇಲೆ ಹೋಗ್ತದ, ಕೆಳಗೆ ಬರ್ತದೆ. One right angle triangle, two right angle triangles, correct? One equilateral ಅಲ್ಲ, two equilateral ಅಲ್ಲ. Bending moment diagram, simply supported beam, uniformly distributed. shear force, center of the simply supported beam, gradually varying load. From 0 at both ends and W at the middle. Hingait load.
WL by 4.
WL by 4. Bending moment ಬೇಕಾಗೈತಿ. Center of the simply supported beam ಗೆ gradual varied load same method. ಗುಡ್ಡ. ಎಷ್ಟು ಬೆಂಡಿಂಗ್ ಮೂಮೆಂಟ್ ಡಯಾಗ್ರಾಮ್ ಇದಕ್ಕ ಈಸ್ WL by 4 ಅಂತ ಅಲ್ಲ ರಾಂಗ್. ನೆಕ್ಸ್ಟ್ ಮ್ಯಾಕ್ಸಿಮಮ್ ಬೆಂಡಿಂಗ್ ಮೂಮೆಂಟ್ ಫಾರ್ ಸಿಂಪ್ಲಿ ಸಪೋರ್ಟೆಡ್ ಬೀಮ್. ಮ್ಯಾಕ್ಸಿಮಮ್ ಬೆಂಡಿಂಗ್ ಮೂಮೆಂಟ್ ಬೇಕಂತ ಸಿಂಪ್ಲಿ ಸಪೋರ್ಟೆಡ್ ಬೀಮಿಗೆ gradually varying load from W at end and W both end and triangle lies in the center, correct? Simply supported beam gradually varied load like same 0 at B and W at A, correct? The shear force at B is equal to ಇಲ್ಲಿ ಜಾಸ್ತಿ ಇರ್ತತೋ ಇಲ್ಲಿ ಜಾಸ್ತಿ ಇರ್ತತೋ ಇಲ್ಲಿ ಜಾಸ್ತಿ ಇರ್ತದೆ ಅಂದ್ರೆ WL by 3 ಇಲ್ಲಿ WL by 6 ಇಲ್ಲಿ answer is WL by 6. For a beam shown 2.43 is the same. The shear force at A is equal to ಅದೇ ಇದು
WL by 3.
right. Next, for the beam shown in same, the shear force at A and B is parabola. Maximum bending moment for this beam ಎಷ್ಟು ಬ್ಯಾಟ್ ಹಾಕ್ಬೇಕು WL square by 9 root 3. Maximum bending moment for the beam shown same lies at a distance L by root 3. Point of contraflexure is a point where ಇದು ಹೇಳಿಲ್ಲಲ್ಲ ಸ್ವಲ್ಪ ಹೇಳ್ತೀನಿ ನೋಡ್ರಿ. Bending moment diagram, if it changes a sign, this is BMD, then this point is called as point of contraflexure. ಕಾಂಟ್ರಡಿಕ್ಷನ್ ಅಂತ ಬರ್ತದೆ ಗೊತ್ತಾ, ಕಾಂಟ್ರಡಿಕ್ಷನ್, ಕಾಂಟ್ರವರ್ಸರಿ. ಇವರು ಮತ್ತು ಇವರು ನಡ್ಬರ್ಕ ಏನ್ ನಡೆದೈತಿ ಈಗ ಕಾಂಟ್ರವರ್ಸರಿ ನಡೆದೈತ್ರಿ ಅಂತ. ಕಾಂಟ್ರಾ ಅಂದ್ರೇನು, ಕಾಂಟ್ರಾ ಅಂದ್ರೆ ಅಪೋಸಿಟ್. ಓಕೆ, ಫ್ಲೆಕ್ಚರ್ ಅಂದ್ರೇನು, ಫ್ಲೆಕ್ಚರ್ ಅಂದ್ರೆ ಬೆಂಡಿಂಗ್, ಫ್ಲೆಕ್ಚರ್ ಅಂದ್ರೆ ಬೆಂಡಿಂಗ್. ಕಾಂಟ್ರಾ ಫ್ಲೆಕ್ಚರ್ ಅಂದ್ರೇನು, ಬೆಂಡಿಂಗ್ ಅಪೋಸಿಟ್. ನಿನ್ನ ನಡ್ಬರ್ಕ ಕಾಂಟ್ರಡಿಕ್ಟರಿ ಐತಿ, ಕಾಂಟ್ರವರ್ಸರ್ ಐತಂದ್ರ ಕಾಂಟ್ರವರ್ಸ್ ಐತಿ, ಕಾಂಟ್ರಾ ಅಂದ್ರೆ ಅಪೋಸಿಟ್. ಓಕೆ, ಕಾಂಟ್ರಾ ಫ್ಲೆಕ್ಚರ್ ಅಂದ್ರೆ ಅಪೋಸಿಟ್ ಬೆಂಡಿಂಗ್. This is positive bending, this is negative bending. This point contra flexure. Okay, next. ಏನಂತದ್ದು, ಬೆಂಡಿಂಗ್ ಮೂಮೆಂಟ್ ಚೇಂಜಸ್ ಸೈನ್, ಕರೆಕ್ಟ್. Shear force at a point is 0, bending moment is maximum. Simply supported beam carrying uniformly distributed load, point of contraflexure ನೆನ್ಪಿಟ್ಕೊಂಡ್ಬಿಡ್ರಿ, ಸಿಂಪ್ಲಿ ಸಪೋರ್ಟೆಡ್ ಬೀಮ್ ವಿದೌಟ್ ಓವರ್ ಹ್ಯಾಂಗಿಂಗ್ ಕಾಂಟ್ರಾಫ್ಲೆಕ್ಚರ್ ಬರಂಗೇ ಇಲ್ಲ, therefore doesn't exist. When there is a sudden increase of or decrease in shear force diagram between 2 points, it indicates that there is a sudden increase or decrease in the shear force. ಅಂದ್ರೆ ಹಿಂಗೋಗಿ 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 ಹಿಂಗ್ ಬಂದಿರ್ತೈತಿ ನಾವು. ಇಲ್ಲಿ ಏನೈತಿ, ಸಡನ್ ಇನ್ಕ್ರೀಸ್ ಆಗೈತಿ. ಇಲ್ಲಿ ಕೆಲವೊಮ್ಮೆ ಏನಾಗ್ತೈತಿ, ಹಿಂಗ್ ಬಂದ್ ಹಿಂಗ್ ಬಂದ್ ಹಿಂಗ್ ಬಂದ್ ಹಿಂಗ್ ಹೋಗಿರ್ತೈತಿ ಶಿಯರ್ ಫೋರ್ಸ್ ಡೈಗ್ರಾಮ್. ಸಡನ್ ಡಿಕ್ರೀಸ್ ಆಗೈತಿ, ಅದ್ ಕೇಳ್ತಾರ. ಸಡನ್ ಇನ್ಕ್ರೀಸ್ ಆರ್ ಡಿಕ್ರೀಸ್ ಇನ್ ದ ಶಿಯರ್ ಫೋರ್ಸ್ ಡೈಗ್ರಾಮ್ ಬಿಟ್ವೀನ್ ಎನಿ 2 points indicates that point load at the 2 points, no loading between the 2 points, uniform distributed load between the 2 points, uniform varying load between the 2 points. Sudden increase or decrease in the shear force diagram antana, sudden increase and decrease at a point alla.
Sorry, point load.
Point load at 2 points. Uh, no load antu alla, no load between point loads antu alla. ಯೂನಿಫಾರ್ಮ್ ಡಿಸ್ಟ್ರಿಬ್ಯೂಟೆಡ್ ಇದ್ರೆ ಪ್ಯಾರಾಬೋಲಾ ಇದು. ಓಕೆ, ಇದು ಕ್ಯೂಬಿಕ್, ಇದು ಇದು ಅಲ್ಲ. ಪಾಯಿಂಟ್ ಲೋಡ್ ಅಟ್ 2 points ಇಲ್ಲ, ನಾ ಇಲ್ಲಿ ಹೇಳಿದ್ದು ಬೇರೆ ಐತಿ, ಅದಕ್ಕೆ ಹೇಳಿದ್ದು ಬೇರೆ ಐತಿ. ಓಕೆ, ಇಲ್ಲಿ ಏನಂತ ನಾವು, there is a sudden increase or decrease in the shear force diagram between 2 points. This is one point and this is another point. This is one variation, this is another variation, ಅಥವಾ this is another variation, both are same, and this is another variation. Okay, this I can consider. This is sudden variation, sudden increase or decrease. This is also parabolic increase decrease, parabolic increase decrease, linear increase decrease. This will be there. This will come when UVL is there in between, therefore D is the correct answer. Okay, when shear force diagram between the 2 point is an inclined straight line, it indicates that there is a uniformly varying load alla, uniform distributed load, therefore no. When shear force diagram is parabolic curve between 2 points, it indicates that A. Sorry, D. When there is no increase or decrease in shear force between 2 points, under constant, it indicates that there is no change in the bending moment between these 2 points. Alla, false. Because if shear force diagram is constant, then bending moment diagram is varying. Which of the following statement is correct? A continuous beam has only two supports at its end. No. Uniformly distributed load spreads uniformly over the whole length of the beam. The bending moment is maximum where shear force is maximum. No. The maximum bending moment of simply supported beam of length L with center point load WL by 8. No. ಈಗ ಎರಡರೊಳಗೆ ಯೋಚನೆ ಮಾಡೋಕೆ, ಈಗ ನಾವು ಯೂನಿಫಾರ್ಮ್ ಡಿಸ್ಟ್ರಿಬ್ಯೂಟೆಡ್ ಲೋಡ್ ಸ್ಪ್ರೆಡ್ಸ್ ಯೂನಿಫಾರ್ಮ್ಲಿ ಓವರ್ ದ ಹೋಲ್ ಲೆಂತ್ ಆಫ್ ದ ಬೀಮ್, ಹಂಗೇನಿಲ್ಲ.
ಎಸ್ ಸರ್, ಕರೆಕ್ಟ್ ಐತೆ ಸರ್ ಅದು.
ಹಂಗಾಯ್ತಾ, ಹಿಂಗೂ ಆಗ್ಬೋದಲ್ಲ. ದಿಸ್ ಇಸ್ ಆಲ್ಸೋ ಯೂನಿಫಾರ್ಮ್ ಡಿಸ್ಟ್ರಿಬ್ಯೂಟೆಡ್ ಲೋಡ್. Uniform distributed load spreads uniformly over the whole length of the beam. This is wrong. Okay, now we'll come to this one. A continuous beam has only two supports at the ends. See, this is also continuous beam. They are not making any sense. This is also continuous. This is not a this one. ಹೌದಾ ಅದಕ್ಕೆ ನೀ ಹೇಳ್ದಂಗ ಬಿ ಆರ್ ಹಾಕ್ಬೇಕು ಒಂದು, ಎ ಆರ್ ಹಾಕ್ಬೇಕು ಒಂದು.
ಸರ್ ಬಿನ ಹಾಕೋಣ ಸರ್, ಅಂದ್ರೆ ಅದು ಎಷ್ಟು ಲೆಂತಿಗೆ ಅಂತ ಕೇಳಿಲ್ಲಲ್ಲ ಸರ್. ಯೂನಿಫಾರ್ಮ್ಲಿ ಡಿಸ್ಟ್ರಿಬ್ಯೂಟೆಡ್ ಲೋಡ್ ನಾರ್ಮಲಿ ಹಿಂಗೆ.
ಹೌದು, ಯೂನಿಫಾರ್ಮ್ ಡಿಸ್ಟ್ರಿಬ್ಯೂಟೆಡ್ ಲೋಡ್ ಸ್ಪ್ರೆಡ್ಸ್ ಯೂನಿಫಾರ್ಮ್ಲಿ ಓವರ್ ದ ಹೋಲ್ ಲೆಂತ್ ಆಫ್ ದ ಬೀಮ್ ಕ್ಯಾನ್ ಕನ್ಸಿಡರ್. ಹಂಗೆ ಹಾಕ್ಬೋದು. ಒಂದೇದು ನಾವು ತಪ್ಪ ಮಾಡಿಬಿಡ್ಬೇಕು, ಯಾಕಂದ್ರೆ ಓನ್ಲಿ ಟೂ ಸಪೋರ್ಟ್ಸ್ ಅಂತಂದ್ರೆ ಅದು ಕಂಟಿನ್ಯೂಸ್ ಆಗಂಗಿಲ್ಲ. ಪ್ರಾಪ್ಡ್ ಕ್ಯಾಂಟಿಲಿವರ್ ಆಗ್ಬೋದು, ಫಿಕ್ಸ್ಡ್ ಬೀಮ್ ಆಗ್ಬೋದು, ಬಟ್ ಕಂಟಿನ್ಯೂಸ್ ಬೀಮ್ ಅಂದ್ರೆ ಮೋರ್ ದೆನ್ ಟೂ ಸಪೋರ್ಟ್ಸ್ ಬೇಕಾಗುತ್ತೆ. therefore B option is proper. Next, match the following. Shear force at a free end of a cantilever beam carrying uniform distributed load.
Zero.
Bending moment at a fixed end of the beam is. Question wrong ಆಗುತ್ತೆ. Next ನೋಡೋಣ. Maximum bending moment of simply supported beam carrying uniform distributed load W. Correct? Maximum bending moment simply supported beam carrying uniform distributed W. WL square by 8. Bending moment at the center of the simply supported beam with gradually varying load from 0 at the both ends, and W, okay, WL square by 12. ಹಂಗಾದ್ರೆ ಇದನ್ನ ಮ್ಯಾಕ್ಸಿಮಮ್ ಅನ್ಬೋದು. ಓಕೆ, ಎನಫ್. ನೀವು ಎಲ್ಲಿ ತನಕ ಸಾಲ್ವ್ ಮಾಡ್ಬೋದು ಅಂದ್ರೆ ಯು ಕ್ಯಾನ್ ಸಾಲ್ವ್ ಇಟ್ ಟಿಲ್ 197 ಕ್ವಶನ್. 197th ಇಲ್ಲಿ ತನಕ ಸಾಲ್ವ್ ಮಾಡ್ರಿ. ನೋ, 197 ಬೇಡ, 196 ಇನ್ನ ಎರಡದ ತಡಿ ಮುಗಿಸ್ಬಿಡೋಣ. Beam, in a beam where shear force changes sign, the bending moment will be maximum. Point of counterflexure occurs in not in cantilever, not in simply supported, yes in fixed, not in overhanging. Bending moment at a section ends tends to bend or deflect the beam, and internal stresses resist in the bending. The resistance offered by the internal stress due to bending is called as bending stress. ಮುಂದೆ ಬರ್ತೈತಿ, ಈಗ ಬೇಡ, ಮುಗೈತಿ. ಇಲ್ಲಿಂದ ಇಲ್ಲಿ ತನಕ ಇದನ್ನ ನೆಕ್ಸ್ಟ್ ಚಾಪ್ಟರ್ ನಾಳೆಗೆ ಬರ್ತಾವ. If you have any doubts, anything you want to share, you can share. No doubts? Shall we end the meeting?
Yes, sir.
Yes. Done. Thank you very much. Good night.
Thank you, sir. Bye, sir.